is what? It's cosine x plus I sine x, yeah? And if these are both 0, then this is equal to 0, which then implies that the magnitude of e to the ix, which is equal to 1, is equal to 0, which is obviously a contradiction, right? So it's really easy to prove that sine and cosine cannot be simultaneously 0 if we have the imaginary exponential to work with. But it's also a well-known fact from trigonometry, right? Sine and cosine are not simultaneously 0. It violates the Pythagorean theorem, right? Cosine squared plus sine squared is 1. You can't have them both be 0 and have them add to 1. So what does this all mean? This means that y not equal to 0 is forbidden, right? It doesn't give us any solutions, so we must have y equal to 0. If y is equal to 0, then what? Well, then we have solutions. Well, that's too easy. That's not true, though. Oh, there's definitely something wrong over here. Oh! Which of these things is not like the other? Which of these things does not belong? There's a sign error in here. There has to be. It should be that we had this should have been a cosh. That should have been a cosh, which means that this was supposed to be a cosh, which means that something funny went on here. Plus oh, 1, 2, 3 minuses makes a minus 1 times I squared makes a positive. This was supposed to be a plus, which made this a plus, which made this a cosh. You guys are supposed to, like, you know, keep me from doing this stuff in class. Like, you know, if students aren't going to correct my mistakes, there's really no point in having students. You know, like, otherwise students are just in the way of lecture all the time. I mean, come on. That's what I was interviewing someplace once ago. He says, man, it's like I could so much covered if there were no students. I'm like, it's true, man. It's so true. It's truth. It's truth right there. Okay, so that was actually, there's no minus here. That's totally bogus. There's no minus. That's just a plus sign. And that was a cosh. Cosh. There, that's more symmetrical. Now you got your sines and your cosines and your coshes and your sinches. I feel better about my day. And although, unfortunately, this is going to complicate the modulus of sine z formula a little bit. So we're going to get, well, anyway, that's no longer true. Sorry, I wish it was that simple. It is not. Yeah, maybe that's homework, so that's good. I didn't do that. All right. Oh, this is definitely true. Yeah. That's true from something called the principle of permanence of identity, which is something we'll eventually prove in here, that essentially if a formula holds in the reals, and if the formula is part of a nice complex function, then the real solutions are all that there is. So yeah, I mean, the real zeros are the only zeros. And we were getting to that here anyway. Look, we're almost there. So we just got that, we proved that y equal to 0, right? And so once we know y is equal to 0, I had gone back up, and so it's like, wait a minute, that's 0, that puts 0 condition whatsoever on x. That's bad. Yeah. So that was not it's actually cosh. And with that, so we get no information on cosine x. That's true.
So it's still positive sine, however.
Oh, yes, thank you. But yeah, and so that tells us that, in fact, we're looking for the solution of sine x equals to 0, which then we know from trigonometry the solution to that is x is equal to 2 pi, n for n in the integers, right? So z equals to 2 pi n plus I times 0 is the solution. It's just what I wrote in the theorem. A similar calculation can show that the only zeros of cosine are integer half multiples of pi over 2, odd integer multiples of pi over 2, like plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, plus or minus 7 pi over 2. We could be here all day. Okay, enough of this. Let us go on. There, of course, is also the cosh and the sinh. So what's the deal with cosh and sinh? What's the definition of cosh and sinh? How do you guys define cosh and sinh?
I mean, cosh is 1/2 e to the x plus e to the negative x.
Uh-huh.
Sinh is 1/2 e to the x minus e to the x.
So what are those? So what I always say is if you take e to the x and you write it as its even part and its odd part, that is respectively cosh and sinh. Sinh is the odd part of the exponential. Cosh is the even part of the exponential. Any function which has a domain which is symmetric about the origin, we can parse into a sum of an even and odd function by this trick, adding and subtracting, f of minus x over 2. But you're right, that's it. And so what do you think the definition of cosh z is going to be? It is 1/2 e to the z plus e to the minus c. And sinh z is equal to 1/2 e to the z minus e to the minus c. Notice that there's no funny business here in terms of like I, right? There's your cosh and sinh. So sine, cosine, cosh, and sinh, these are all built with the complex exponential function. And the properties of all these functions ultimately rest on the properties of the complex exponential function. Very simple. Very simple. There are specific relations that intertwangle the cosine, the sine, the cosh, and the sinh. Can you see how they are related? Like, check this out. If I do cosh of, let's say, iz, that gives me 1/2 e to the iz plus e to the minus iz. What's that? What? Argument? I'll take a cosine z. Yeah, that was by definition cosine z. See, it's up there.
Where? Oh, yeah.
And what happens if I look at sinh of iz? We've got 1/2 e to the iz minus e to the minus iz, right?
Minus I sine z.
Is it though? There's no I there, right? I mean, you're on the right track. But so to be fair, I can multiply by 1, right? A good way to multiply by 1 here is to divide and multiply by I. So if I divide by I here, and I multiply by I over here, then this piece, as you just said, is sine. And so we get I times the sine of z. Now, of course, we can also take this equation and solve it for sine z, right? Sine z is equal to minus I sinh iz. That's true. So there's a minus if we look at it that way. But so cosh and sinh and sine and cosine they're almost the same functions, really. I mean, that's not quite true, but they're very related. Like, take this for example. Solve sinh z equal to 0. Well, sinh z is actually what? Aw, man. Rats. I think I need to go the other way. Let's try this out. So what is, sorry, I need to do like, what's sine of iz? So that's 1 over 2I e to the I iz minus e to the minus I iz, which is what? 1 over 2I, 1 over I times 1/2 e to the minus z minus e to the z, which is actually minus I times minus the sinh of z, which is I sinh z. Which isn't quite what I want for this problem yet, but you see I can trade sinh z. Sinh z is what? It's actually equal to minus I sine iz, right? By the algebra there. If I solve for sine iz. If I solve for sinh, rather, I get minus I times sine iz is equal to sinh z. So see, if I look for where sinh of z is 0, that's the same as looking for where minus I times sine of iz is equal to 0. But I can simply make a substitution and solve this the same way we just did in example 7. So the only solution to this is going to be, we get iz is equal to like 2 pi. Oh, not 2 pi. There's no 2 pi here. I'm a dummy. Why did I put a 2 pi up there? What do you guys let me do this for? I'm going to have to get some new students. This is not working. You guys, if you guys don't find my errors, like, come on. I mean, you have to find my errors, peoples. Otherwise, the internet will find them later, and then that's annoying. I wonder if I could start charging for making comments. I don't think that's a feature of monetization, like 25 cents for a comment. That'd be handy. I don't think YouTube has that yet. Maybe I should suggest that as a future feature. Anyway, so the solutions then are z is what? Is equal to minus I pi n. In other words, so basically I pi z, an element of that is a solution to this equation. So, well, that's a little bit more interesting, isn't it? We know that the real hyperbolic sine has only one solution, namely the 0 solution, right? But the complex hyperbolic sine has countably many zeros. And they're all along the imaginary axis. The one which we know at the origin, and then an infinite family of them going up and down. All right? Oh man. Rats. I see our time has come to an end. It's so sad. I wanted to tell you guys about complex powers, but I guess I'll have to do that another day. But actually I probably shouldn't, because you might have homework, but complex power z to the power p is defined to be e to the p log z. So I think that's the main thing I didn't get to today. The complex power, it's actually not one thing, it's a set of things, because it's a little logarithm. So, and as I describe in the notes, it often has two tails. It'll have one tail that goes to like the origin and have another tail that goes off to infinity. Which of course leads me to the question, is there a math with more tails? Like it's only a two-tailed beast, this complex power function. You know, could you find like a nine-tailed power function? I'm sorry. You guys don't enjoy the finer things. You don't know what I'm talking about. A nine-tailed beast, it doesn't mean anything to you, does it? Go ask your brother. He'll tell you. He is wise. Yeah, your brother will tell you. Surely your brother knows about nine-tailed beasts. Ask your brother if he knows what a nine-tailed beast is.
Right now?
You don't have to ask him right this second, but you could like, you know, text him and then let me know what he says.
Okay.
Yeah. All right. Anyway, so yeah, this is the complex power function. This will reduce to like ordinary integer powers if we put in like p is a natural number. It reduces to just the usual power notion, and the set, like this set of functions, set of values thing goes away there. But I wanted to just throw that out because there may be a problem in the homework that you need that definition for. But I think I've covered pretty much everything. So next time we're going to start with topology and limits. I think I've told you guys enough about the functions that we can go on from here. And if we need to cover any of the background that I missed, we'll come back to it when we come back to it. As always, do please read my chapters because I try to get everything in class, but I just never cover everything, you know? So, hey, that's why there's homework.
And we have the mission next time.
Oh yes, do turn in your mission next time.